Right now I'm just going to leave it as join, and the profile I want is that portion, and I want to keep it symmetric about where it's placed. Give it a distance and accept that. Now I can see I've got that portion. I want to go ahead and just make it slightly different. So I'm going to say the properties of that feature, I'll just give it a different color. That way I can see the difference and designate the difference there. And I'm going to go ahead and just return. And we'll see the assembly now. Let me just zoom in here. If I play, we'll see the actual path following there. Sorry, get that in a view where you can see. There we go. And it's still adding that trace, and I don't necessarily want that trace in there. So I can go back to the output grapher, go into that trace. Since I'm done with it, I can simply delete it, close my output grapher, and go ahead and replay that thing. Then if I want, I could actually sit here and just let it be cyclic and watch it play. And we can see it's getting the motion we want. We're getting the opening and closing of the valve in the desired form. So I'm done with this portion, and what I'm going to do is send this over to John Ulrich, who's going to take this and do a FEA analysis study on it. So bear with me for just a second as I change presenter to John.
Thanks, Jason. You want to let me know when you can see my screen there, and we'll go ahead and get started with the remainder of this.
Okay. Yes, indeed. I see your screen, John.
All right, excellent. So basically what Jason did in the first part of this demonstration was to go through and create a cam that was going to give us the desired motion on the valve. And so his use of the simulation environment was to provide the exact motion of the valve that he wanted as it opened and closed, and then come back and create the cam from that. The next step that we want to do here is to kind of reverse that and force the cam to actually generate the forces that are going to be needed to cause the valve to follow that path. So to get there, what we want to do is go into the joint that Jason had set up here, and for those properties there, we actually want to set this starting point to 0, and we want to go in and turn off the imposed motion on that so that that joint is just free to float. And basically that's just going to allow the cam to be pushed open as the valve to be pushed open as the cam comes around and pushes on the follower. So what we want to do next then would be to create a couple of more joints to drive this assembly. So we'll go into our insert joint tool, and we're just going to add first a spring, and we'll just place that spring here between the two faces of our cam, or our valve seat there, and our valve guide, I guess it is, and the valve itself. And we'll place that spring on there, and we also want to create a 3D contact between the cam and the cam follower. So I'm just going to go over here and click on the surface of the cam and the surface of the cam follower there. And that way, when those two parts come in contact with each other, they won't be allowed to interfere, and therefore the cam will actually drive the location of the cam follower. We also want to make a couple of changes here to the properties of that spring. So instead of that diameter of 4, let's give it a diameter of 10 millimeters there. And the stiffness of that spring, I want that to be about 5 newtons per millimeter. And as we can see, the free length defaults to the actual distance between those two surfaces that I picked. And I actually want to run that out to, let's call it 35 millimeters, so that we've got some preload on that spring when the valve is in the closed position as it is now. So I'll say OK there, and we are now ready to go ahead and run the simulation, and that's going to drive this whole mechanism around just by rotating that shaft, and we're still using the imposed motion that Jason created to turn the shaft at 60 revolutions per minute, which of course is chosen so that we get that one revolution in the 1 second that we're looking at. And as you'll see here, when the the cam comes around and starts driving that cam follower up that cam lobe, we compress that spring and open the valve. And of course, we're going to have forces as a result of both the spring and as a result of the accelerations and the momentum, or the moment of inertia, and the inertia of these different parts in this assembly. So when we're done with this, what we'll see will be an accurate representation of the forces that are needed in order to get the motion that we just saw on the screen. And to look at those, of course, we're going to click over to our output grapher, just like we saw Jason doing a minute ago here. And as you can see in the upper right here on the output grapher, we've got a big long list of all of the time steps that go into this simulation. And what we want to do is we want to look at a couple of different things. Right now we're tracking the position of the valve against those time steps, but we also want to take a look and see what the force is in the two joints that are actually pressing on the on that rocker arm. So what we're after here is we're going to take and do a finite element analysis on that rocker, and we want to see what the deflection is going to turn out to be, and try and optimize the design of the rocker so that we aren't having using too much mass there. So we're going to try and go through and run that finite element analysis, but we want to take advantage of the fact that we can see the maximum values of these forces here. And I'm just going to right click and say search max, and I'm going to find the time step at which the maximum force occurs on each one of these forces. And I can do that on either the force in the cam follower or the force in the valve stem itself where it contacts that rocker. And I'm going to go ahead and grab the one that is the highest for the cam follower there. And I'm going to check this box over on the left-hand side, and you'll notice that this column on the left says export to FEA. This is going to allow us to take as many of these time steps as we want to, check the box on each one of them that we want to examine, and just export those out to be used in a finite element run. And for that, we're going to need to identify what parts we're analyzing. And in this case, it's just going to be the rocker. Could be multiple parts, could be every part in the assembly, really. In this case, I'm only really interested in the rocker because the valve stem and the cam follower are kind of simplistic. And I'm just going to quickly go through here and identify the faces that are associated with each one of these joints. And we've got contact joints set up between the cam follower and the rocker, as well as the rocker and the pin that it's rotating on, and then also the valve. I could use an automatic face selection here too, but this is kind of quick to just go and grab those three and let you see that. So having made that selection, I'm going to go ahead and exit out from the dynamic simulation environment, and we'll jump across to the stress analysis environment. And here in the stress analysis environment, we're basically going to start up on the left-hand side of the ribbon bar, and we're going to move across until we get over here to the report. So we'll start by creating a simulation, and we could do a single point simulation, or we could also come in and say, I want to do a parametric dimension for my design objective. I'm going to modify a parametric dimension, and I'm going to see what happens when I do that. So for my static analysis here, I'm going to set this up as a motion loads analysis, and you'll notice that it knows which part and which time step to look at. If I had multiple parts or multiple time steps, I could select which one of those I was going to look at this moment as well. But right now what I'm going to do is just grab that one time step that we pulled from the simulation environment, and we're going to set the contact between the various parts of the assembly to use separation, which means at the moment any two parts that are within 1/10 of a millimeter of each other, or any surfaces that pass within that tolerance, are going to be established to have a separation type connection between their two meshes, and that's going to allow the math that runs behind this simulation to accurately represent the real-world interaction of the parts in my assembly. So the next thing I'm going to do here after I've established my loads and constraints, essentially by pulling those in